topics and then open it up for questions. But before I do all that, I wonder if any other questions about logistics or anything like that. Yes?
Do we have any responsibilities after Tuesday?
No.
Is the exam here?
We will be letting you know that it's going to be partly in this room, but we didn't think there's enough space for everybody, so we're going to have a couple of other sites as well. We'll let you know. It's going to be a paper-based test. We decided to try that. Doing edX is challenging. The exam was less auto-graded this year than it was last year. This was less auto-graded this year than it was last year. So there would be no calculators, but that's what we do. What's that? I think it's in the syllabus. Basically every part of the course contributes some fraction of your final score for the class, and then we're going to determine grades once we see the complete picture of the score of everybody's grades. So we're going to globally curve. So does that make sense? So that because we'll look at all the project grades and the homework grades. I'll look at all the project grades and homework grades summed up, and then I'll decide where to make the class. We're going to look at the borderline cases. Yeah.
So the grade of the final exam will get an average of 2 parts.
No, each part will contribute half of the points of the final. And then each question is going to be clearly labeled with how many points it is. Yeah.
That the system chooses the lowest bookmark for the wrong. I'm not sure.
Can you turn on your mic?
Oh, my mic. All right. More questions? Yeah. No calculators. We'll keep them in arithmetic. It won't be 0, but it will be minimal. Any more questions? All right, so this is a course, Applied AI. So the goals of the course, which you can tell me if you think we've achieved them. I want you to successfully understand theoretical and practical approaches for building intelligent systems, and we've kind of covered a spectrum of those approaches throughout the course. Describe and implement searching and scoring algorithms for producing intelligent behavior. So we've talked about that theme has kind of come back throughout the course from breadth first search and our models for uncertainty, and then at the end when we're doing sequences of decision making under uncertainty with MDPs and RL. And then use AI techniques to solve real world problems. So you saw that through the projects, SLAM and searching in Pac-Man for games, and decision making, computer vision, and the email stuff, and then the RL project that you guys just finished. And we've also done a number of case studies of research papers and also applications of AI in other parts of in sort of real world applications. And my goal for this is to try to help you guys see the connections between these ideas, these technical ideas that we're learning in class, and how they actually play out when you encounter real problems in the real world. So that when you go off after this course and you encounter a problem, you can kind of see how there's like this theory, there's this nice algorithm that's kind of abstracted away. But a lot of the hard work is kind of figuring out how that abstraction applies to some concrete problem. And it sort of changes how it happens in different ways. And we saw a number of examples of that. So we sort of started out with, what is AI? This is the wrong slide deck, actually, guys. I apologize. That was my first slide deck I was copying. That was way at the beginning. We talked about what is AI, different definitions for intelligence. And we got to this algorithm for all of AI, for how to act rationally. And this is very abstract, right? We're going to search through all the different actions. We're going to somehow score the actions, and then we're going to pick actions that have a good score. And we talked about lots of different ways of carrying out that search, how we define the space of actions, how we can search deterministically or stochastically, how we can apply knowledge to search, to target our search in better parts of the search space, how we can define that scoring function. So with our models for uncertainty and for machine learning and for reinforcement learning, so how can we acquire this knowledge about what to do that summarizes information in the future to make good decisions now. And then we had these modules for the course, right? So that there were different implementations of this. So we had search and planning, the Pac-Man project, uncertainty, so that was Jaynes and the probabilistic reasoning, and then the project was SLAM, so trying to make a robot that could localize itself in a map and also construct the map all at the same time using a particle filter. And then making a decision. So that was the spam filtering and also the door detection. You guys did a number of different machine learning algorithms as part of that project. So you got a sense for discriminative versus generative models, and then models that kind of just that don't build that sort of don't use probability at all. They just kind of do the right. They try to do the right thing. ROC curves for deciding where you want to put that cutoff based on utility. And then that kind of brought us into making sequences of decisions, MDPs, and reinforcement learning. So that was the RL project. The robot is running around in the environment and trying to figure out actions that earn reward over time. Value iteration, Rmax, Q-learning, and all that stuff. So that was the sort of content that we covered in a nutshell. So the rest of this deck is kind of just summaries of all the stuff we did, breadth first search, depth first search. And I can go through it, but maybe I'll stop now and ask you guys if you have any questions about anything. Or there's topics you'd like me to cover in more detail in the review. Things you'd like to hear more about. I can keep talking, yeah. When to use model-based versus model-free. Yeah, that's good. So what do you think?
The only trade-off I can really think of is memory. Like, you need a lot more memory to build up your models of like transmission of rewards in the environment.
So you can think about model-based versus model-free in RL, but you can also think about it in just sort of regular machine learning when you're making a one-off decision. And the same kinds of trade-offs happen in both. So maybe I'll ask you guys. So like memory is one. Like, so if you are doing something model-free, maybe you've got to save up all your training data in order to create the model. Where if you're using model-based, it depends on the model, right? Like it might be able to summarize the data in a smaller form. So it might use less memory, or it might use more memory. Like it might be that your model is big and your training data set is small, and then you might be in trouble because you might not have enough data to set the parameters of your model. Or it might be big because you've put a lot of knowledge into it, and that's augmenting your training data. So maybe we can hear from more people in the class. So when should we use model-based versus model-free? What's the reason to use model-based? Yeah. Maybe I'll put this up and write things down. So model-based and model-free. So when you think you know a good model? Maybe before we start with reasons, maybe we should just define them first for people who might not remember. So what is model-based? Model-based RL or model-based machine learning? What does it mean?
That was like the Rmax algorithm where it's actually trying to understand what's happening in the world and build rules.
Yeah, Right, so RMAX is an example of a model-based RL algorithm where it's trying to actually build up your transition dynamics and your reward function explicitly. Right? We're trying to learn what the transition dynamics are, we're trying to learn what the reward function is, and then act according to that model. We're imposing our ideas of our structure on what we think the model should be learning. So I'll write RMAX as an example. RMAX. And what about model free? What's model free? Somebody else. Yeah, yeah. Maybe somebody wants to expand on that a little bit. He said just trying to learn what the best thing to do is in this state. Yeah. Yeah, Q learning is the example. So we'll write that one down. Q learning is one of the examples. There were a few more we covered in RL, or at least one more. That was model free. Policy search, yeah. Policy search. So thinking about policy search, so why is policy search model free? It's related to, yeah, in the back there.
Just trying to find out what action is taken in a given state, not trying to find out.
Yeah. Yeah, so in RL, you would say this is model free, both of these are model free, because you're not trying to learn the transition dynamics and the reward function, right? You're just trying to pick the action directly, or you're trying to estimate the value function. So this is kind of assuming a little more structure about the world. This is just saying, just pick the action. I don't care about maximizing my expected discounted reward. Maybe I do care, but I'm not going to tell my algorithm about that. I'm just going to tell my algorithm to try to pick good policy parameters that do the right thing. And sort of go from there. Now, within policy search, though, I could still have a model, right? What would that look like? So if I'm doing policy search, I want to do model-based policy search.
I think the model is just for policy, not for the whole problem.
Right, right. So what might model for a policy look like? What's an example of? There's several different ones. There's lots of them. Distribution. Yeah. So maybe it'll help to think of like a specific problem. So like let's imagine I'm doing a grid world problem where I'm trying to find a path that reaches a goal, and I'm doing policy search in that space. So what might a policy look like? What are some assumptions I might make about what are good policies? So my actions are going up, down, left, right. There's walls, and there's pits that I could fall into, and there's places where there's really good reward. Like, what is some information I could stick in there to make a policy search algorithm work better? You could think about it as like features. What are some features you might give it? So like, I'll draw a picture. So here's my little guy, my little agent. Here is a pit, and here is a treasure chest. And I'm going to walk around. I can go up, down, left, right. There's walls. There's some kind of transition function. Maybe I slip sometimes, so if I go forward, maybe sometimes I go right. And I could do Q learning. We talked about that. This is kind of like the problem that we covered in examples of the grid build problem from the textbook. So now I'm going to try to do policy search. I'm going to try to come up with a policy for this that by directly having some distribution over the actions, P of A given S, given my state. That's what I want to learn directly. So it's model-free RL, because I'm not going to learn the transition function and the reward function, but I can still have a model. So what would I do to have a model in there? What are some features I might use if I was doing some kind of feature-based method? Yeah? Yeah, so that can be the supervision, is the immediate reward. So that's like the Bronovan paper, right, where we kind of move our parameters up and down based on how much reward we're going to earn. But what am I going to, like, what are some ways that I could model this, right? Like, what's that?
You can represent it.
Yeah, how can I represent that distribution? So like this looks kind of like our machine learning problems, right? So what are some ways what are some things I could do from our machine learning unit? You can just pick an algorithm from the unit, and you'll be right. So what's something I could do? Yeah.
We can assume a distribution with some parameters and
Yeah.
machine learning, or we can do like regression.
Yeah.
Or we can do like particle filters.
Well, let's assume that this is discrete. There's 4 actions here, right? So that's my class label, and there's a state. I mean, I could represent that in lots of different ways, right? And so I sort of have a machine learning problem, right? Like I have a class from a discrete set, and I have something that could be a feature vector. So how could I learn that model? How could I represent that model? How could I parameterize it? Yeah. Yeah, so like we were naive Bayes is one example, right? Like I could do naive Bayes. Naive Bayes. What else could I do? What else could I do? Decision tree, yeah, I could. Decision tree. Decision tree. What else? What else? Logistic regression, yeah. And there's more, right? Like you can pick logistic regression. You can pick your favorite model to do this. And somebody back there said we could do a Bayes net, right? Like we could impose a structure, an arbitrary structure. So a naive Bayes is one particular Bayes net that factors in a particular way that lets you use features, right? So we would somehow featureize our state. We'd say something about like if you're standing near a pit, maybe some actions are bad. You know, so that might be a feature that you give to this model, and then it learns that that feature weight is predictive of good or bad actions. But you could also impose structure in a different way by doing an arbitrary graphical structure, and people do that. So within this, so it's kind of a tricky term, model-based and model-free, because within model-free RL, where in RL, like the model it means the transition dynamics and the reward function. So model-free RL says I'm not going to learn those things. But if I'm doing policy search, I could still have a model. I'm not using it to model the MDP, right? So it's not model-based RL, it's model-free RL. But I can still impose my knowledge about the problem into the system in different ways. You have a question?
Yeah, I was wondering why we look for a distribution on A.
Mm-hmm.
Don't we, that's a policy distribution.
Yeah, that's good. So that's a good question. So why are we looking for a distribution on A? So here I wrote down probability of A given S. And really, what we want is we just want to know A, right? Why is it better to know A than just have a distribution on A? Why would it be better if we just knew what A was instead of imposing a distribution on it? If we're trying to act optimally and earn reward. Yeah. Yeah, it's like exploiting. We just know what to do. We would know exactly what action to take in every situation. If this was not a distribution, or you could say it's a distribution, but like it's all zeros and ones. There's one action that I should take, and all the other actions are zero. And then it would be a deterministic policy as opposed to a stochastic policy. I know exactly what to do in every single state. I look it up, I do it, and then I do the next action, the next action. And it's not, if I know exactly what to do and I do it and it's right, everything is great. So why do you think we go talk about these stochastic policies? What's the advantage of using a probabilistic representation here for this? I want other people to see your hand. What's the advantage of a stochastic policy? So what's going to happen when I'm learning this model? Yeah?
We might not know what.
Yeah, as we're learning the model, we might not know what the right action is. And so by writing it as a distribution, we're kind of explicitly acknowledging that. At the beginning, we might have a very uniform distribution. And then as it's learning, it may acquire more evidence about what good actions to take. But it might never converge, or it might sort of converge over time. This lets it explicitly capture that uncertainty. Yeah?
So when you're at a given state, and you're sort of deciding what action to do next,
Mm-hmm.
is it should you like sample from that distribution, or should you pick one of the maximum?
People do both. People do both. So it gets back to the explore versus exploit trade-off. So the question was, if you're in this distribution, and either you're learning or you're not, are you supposed to sample from the distribution, or are you supposed to pick the best action from it and just go with that? And people will do both. And you can also build an epsilon greedy into this. So you can say, well, I'm going to use this maximally the best some of the time, and other times I'm going to do something random to try to make it explore in a better way. So what's another reason we might want to use the stochastic distribution instead of having a deterministic policy all the time? Yeah?
It may not be a determined word. So
It's what?
it may not be a determined word, so the action might cause some randomness.
Yeah, there might really be multiple different actions that are optimal. And so the underlying domain might be stochastic. And so in that case, a stochastic model is going to better capture what I can be doing in the world. So does that answer the question?
Yeah.
Yes, good. Cool. So that was a good question. I forgot who asked it, but it was good because it kind of connects across different areas of what we were covering in the course. All right, so maybe what I'll do is kind of start flipping through slides. We can see. I'll leave the board up. So we talked about formulating a problem, state, the actions. What else? You remember what else? What's going to be next? Transition, yeah, transition. Hear it? Results. And in the beginning, it was deterministic transition, right? And then at the end, it was stochastic. This was like the RL or MDP model of this. Goal test. At the beginning, it was just a state identifying a goal. At the end, we had a reward function, right? So at every state, you could get some reward or some negative reward, some punishment. And it's trying to optimize its reward over time. How could you encode this kind of, so this kind of goal test where there's one state, how could you encode that in a reward function? If you wanted to define a reward function that was the same as this kind of goal test, what would you do? Yeah, you'd only give it reward at that single state at the end. and then sort of let it go. If you discount it, then it'll make it try to get there as soon as it can. There's other ways too. You could give it negative reward for being alive and 0 reward at the state that you want it to end up in. And so then it tries to get to that state because it wants to stop getting the negative reward that it gets for being alive. And then you can have a path cost. So this was the cost of transitioning to different states. And again, you can bake that into the reward function in MDPs. Talked about uninformed search, breadth first search, depth first search. So that was like, what happens when you do depth first search in an infinite state space?
Never get a solution.
Yeah, you might never get a solution. Why? What's it going to do? It's going to go off down one tangent and just never come back. And if it got unlucky, that might not be the right thing to do. When might that be the right thing to do? What kinds of state spaces would that be okay? Somebody else. Somebody from this side. You guys have been quiet. So depth first search in an infinite state space. If I run, I might go off all the way into infinity and never find the answer. Whereas breadth first search, what's breadth first search going to do in an infinite state space? It's going to kind of do this expanding cloud thing, right? And kind of cover everything. So it's going to it's going to get to the goal eventually, although it might have to expand a lot of nodes to get there. No? Okay. So when might I, even though depth first search might go off into the wild blue yonder in one of these infinite or really large state spaces, under what conditions might I want to use it anyway?
Well, if your goal is like a ring or something,
Yeah.
or like if in any direction, if you go like 10 meters away, if you get to the goal, then
Yeah.
depth first will get there much faster.
Yeah, so if you have lots and lots of goals out there, any direction you go, you're going to hit it, but maybe it's going to be a while. Then breadth first search is going to do this coverage thing, and it's going to kind of expand its cloud, and it'll find all the goals at once, but it might expand a lot of nodes to do it. Whereas depth first search is going to shoot an arrow, it's going to hit a wall, and hopefully that wall is a goal, and you'll get there. And then there's variants of algorithms that kind of blend between the two. So you can do depth first search to a fixed depth, and then stop and come back and then try it again. So you can sort of get at some of the advantages of both. Iterative deepening search. All right, then what did we talk about? Uninformed search. There was informed search. So what was that? What's that? Yeah, so right, A star, UCS, and A star. So greedy search, Dijkstra's algorithm, A star search. So what was the intuition behind those types of algorithms? What was the reason we wanted to do, let's say greedy search as an example? Yeah, so there's this thing that we called a heuristic that said something about what is the relative quality of different actions in the state space. So it was some guidance that we had, that we gave to the algorithm that said, this is a good idea, this is a less good idea. And that enables the algorithm, by using that information, sometimes it can do much better than uninformed search. So you can think of depth first search as this kind of expanding cloud. You know, what's a heuristic-based version going to look like? Yeah. Yeah, it's going to expand in a particular direction. Well, how is it going to get that direction? Somebody else. Where does the direction come from? From the heuristic, yeah. So the heuristic sort of gives us guidance on what are promising directions to search for. And then we had greedy and A star, right? So remember, so anybody want to say what those two algorithms were? So what was greedy? Yep. Yeah, always take the best heuristic value, and just go for it. try to go down the hill until and hope that that leads you to a good place. So what's good and what are some good things and some bad things about greedy?
It's a short-sighted algorithm.
It's short-sighted. So what do you mean by that?
Well, it doesn't account for the fact that a decision you make right now might hurt you down.
Yeah, so it's just going to try to pick the best heuristic value and go for it. So if it's wrong, you might not find the optimal trajectory. So that's not so good. What's good about it? Or what are other bad things about it? Yeah.
Well, one thing that's nice about it is that it's not that computationally intense. If it
Yeah.
is generally okay for what we're doing, then we can go very quickly.
Yeah, if you have a good heuristic and it's a really big space and you just go, right? Like it might be, and you don't care about finding the optimal trajectory, you just care about finding a solution. Greedy can really work for you. And some of the best algorithms, some of the coolest algorithms in AI are based around this idea of greedy search with a good heuristic and a well-defined search space. A lot of the advances, when people get things running on real systems, greedy is where a lot of this magic happens, where we don't know that we found the optimal solution, but we found a pretty good solution, and look, it works on a robot, or look, it worked to do playing these Atari games, for example. All right, so tell me about A star. Yes?
Heuristic plus path cost.
Yeah, it's this combination of heuristic cost plus path cost to figure out what action you should take. If you remember, we had this sort of sequence of algorithms where we started with breadth-first search, and we added the path cost, and we added the heuristic cost, we got greedy. We added the path cost, we got Dijkstra, which gave us the optimal algorithm. And then we added the heuristic cost plus the path cost, and we got A star search. So what are some good things and some bad things about A star?
It's optimal as long as the heuristic is admissible.
Yeah, so we can, unlike greedy, it's provably optimal, right? As long as our heuristic is admissible, as long as our heuristic doesn't lie to us, then A star is going to find the optimal solution. Good. Yeah? Can A star handle negative path costs? So that's where like you go through a teleporter and it kind of eats your past path costs. It's an interesting idea. I bet that it could. I bet that it would just work out, but I'm not sure. I think I have a feeling that if you just added a constant to all your path costs to make them all positive, it would just be the same. But I'm not sure. I haven't actually coded it up and tried it. It'd be kind of an interesting world where you could do that. Like, you could. It's like a speed boost when you play a video game. You go and you end up farther than you should have gone. Yeah.
Negative path costs mess up consistency.
Well.
Depending on how what.
Yeah. I mean, you have to have. I mean, maybe I think I have this here, so we can stare at that and think about it. So the cost of going from n to a to n prime, if that was negative, I think it would make it easier to make like that would make that left side smaller. Yeah.
As long as your heuristic function is still admissible, it's all right.
Yeah, I think so too. I think that's likely to be true. As long as this inequality holds, so it's going to mean your heuristic is going to have to respect the negative path costs. I think it's going to be okay.
But Dijkstra cannot handle inactive edge.
Can it not?
Dijkstra.
Okay. Then maybe A star. I don't actually know. I think the right thing is for me or somebody to sit down and try it and code it up and give it a test and see.
Maybe it depends on like how the algorithm say if the state is visited. So
Yeah.
probably at the beginning, because it's inactive and the heuristic may not. I mean, I'm not sure, but
Yeah.
maybe it does not go through the inactive edge, and it's already arrived at state, so it will not try other paths.
Right. So if it's like a real, so if you think of an extreme example where there's like a really negative path cost, it's going to be really hard for any other edge to outcompete with that, but that's kind of okay, right? Like if it's a really
Not sure.
negative path cost, like you really want to do it, right? Like you really want to get that win from the negative path cost. So it seems like it might be okay. Yeah? What's that? Yeah, that would be bad because you would just go around and around. Like the optimal behavior might be to never hit the goal, but just go around and around and around. Yeah, that sounds plausible.
Dexter's can't have negative path costs because, like, every
Uh-huh.
node when we visited it,
Yeah,
we are guaranteeing that we found the shortest path to that node.
I see.
But if you have a negative path cost, then there could be a shorter path. So, like, if like the cost for node A is 2,
Uh-huh.
and node B has x from B to A, cost of B is like 3,
Uh-huh.
then B to A is -2, then the cost for A is now -1. So we would explore past A when we're not actually in the shortest plan.
I think I see that. I'll send an email about this issue, and it will not be on the exam. Good question. All right, so we talked about heuristics, admissible, consistent. There's examples, so like the Manhattan distance. Yes?
I was just wondering, what's the difference between uniform cost search and Dijkstra's? Like what
Yeah, so
extra they star those and uniform cost search, like what are the differences?
yeah, so uniform cost search is like when the cost to go to one node to another node is always the same. So then you get so breadth first search is an example of that, where you are it's basically the algorithm running Dijkstra's with cost of 1 reduces back to breadth first search. But when you have non-uniform cost, then you want to find the shortest path, not just in hops through the graph, but like based on the weights between edges in the graph. Then you do Dijkstra's or A star if you have a heuristic. So we talked about coming up with heuristics. You guys did the Pac-Man project. You came up with lots of heuristics for eating food and visiting the 4 corners and stuff. You code them up and admissible and consistent. These are some examples from the 8 puzzle. We talked about relaxed versions of the problem and how that can lead you to heuristics. So you take away some of the constraints of the problem. So imagine that you can teleport tiles around in this puzzle, and that gave us some heuristics. And the reason that relaxed problems were nice was that it enabled us to estimate some kind of lower bound on the cost of solving the problem quickly. So a relaxed problem is one where we wanted to find relaxed problems where they were easy to solve. We could solve them fast. And then use that fast solving to get a heuristic value that somehow correlated or estimated the cost of the full problem, which we didn't know how to solve. If we did know how to solve it fast, then we wouldn't need to do A star. It's like this chicken and egg kind of thing. And we talked about plans versus policies. So this was like alpha-beta pruning, minimax and alpha-beta pruning. We played tic-tac-toe in class. So what's a plan? What's a policy? It's kind of up there. When might you want a plan and when might you want a policy? This is related to the question about deterministic versus non-deterministic. Yeah?
You know what's going to happen to your action.
What's that?
You know what's going to happen to your action for sure.
Yeah. Yeah, so if you just know the world really well, then you can just make a plan. And it's going to work because you're just assuming that you know what's going to happen. Yeah?
If the world's deterministic, the plan.
Yeah, so another way of saying that is if the world is deterministic, if I assume my model's true, then I can just find a plan. And I take the action, and I know that's going to lead me to the next state, and everything's going to be OK. In contrast, tell me about a policy. When would I need a policy? When do I want a policy?
When the world is not deterministic, we may end up somewhere different than where you expect.
Yeah, so if I'm in a non-deterministic world, so if I'm in an MDP and the transition function is non-deterministic, then I need a policy, because I don't get to control where my next state is, and I need to know what to do when I'm in my next state. So what are some advantages versus disadvantages of plans versus policies in that world? So like, let's imagine I'm in a non-deterministic world, but I've got a plan. What's that? It might not get to the goal. I might go off the beaten path, and then I might not know what to do. But what's nice about a plan? Let's imagine it's a really, really big world. Yeah.
If you have a plan, you just have constant time going following it.
It's kind of like a roadmap, right? So if I have a really, really big world, but like I just want to get across the room, let's say, and there's a really big, it's a really big room, the plan's going to be a lot smaller. It's going to be very compact. It's just going to say, do this, do this, do this, do this. And if I get lucky, maybe I'll be okay. Maybe it'll be good. What if I get unlucky? What can I do? Am I done? So I decide I'm going to not have a policy because I don't want to think about every single state in my world. I'm just going to have a plan, and then I try it, and the first time I do an action, it does the wrong thing, and I'm stuck. What can I do? Yeah.
I mean, if you know you've done the wrong action, you try to undo it.
Yeah, maybe I can try to undo it. Maybe I can put that into my plan somehow. So I could redefine my state space to try to make it more deterministic. So by adding, for example, by adding an undo action, or by having a kind of more abstract action that says, I want to get here, and I'm going to somehow find different actions. If the first one fails, I'm going to have some backup actions. So you can. It's not so what you're getting at is it's not like these are kind of two extremes, right? A plan is like one sequence of actions. A policy is what to do in every single state. But you could have a partial policy, right? You could say this is some things to do in some states and still haven't figured out what to do in every single state. So you can kind of get a relaxed version of that. You can think of it as a relaxed version of either one. Like it's something in the middle where it's got some actions for more than one state. It's got some failure recovery, but like maybe if you get too far off the beaten path, then you're stuck. What else could you do with plans? Just plans in non-deterministic worlds. Yeah, so if I have an ability to make a plan fast, I can just do it again. So if once I can detecting that I got somewhere bad is crucial. But once I've detected that I've gotten off my plan, I can just run my planner all over again. So that algorithm is called forward search. Whenever I get off the beaten path, I run the planner again. I assume it's deterministic, or I find the most likely single sequence of actions that gets me there, and I start again. So it'll, now I'm here, it's just going to try to figure out what to do, and if that one gets off the beaten path, I'll do it again, and do it again. That's actually a very effective algorithm for big state spaces, and a lot of people use variants of that for robot controllers and also for solving MDPs quickly. So, yes? Forward search. Or people also call it model predictive control in like controller space. So you just run the best thing and run it till you get off the train, and then run it again. To make it work, you've got to do it fast. If you're trying to like move a robot with it, people actually do move robots around with this. So you have to be able to run the planner really, really fast, so you can get a new plan and then start executing it quickly. But it's a very natural algorithm. You just need a planner. You don't have to do this whole policy business. Although policies are good too, right? Like, so in situations where it's costly to do a plan, and where maybe the state space has structure, or it's small enough that you can actually get the whole thing, then maybe you want a policy. So we talked about, this was in the context originally in games, right? So in that world, the transition function was non-determinate. Maybe it was deterministic. It depends what you assume about your opponent. But the point was you didn't get to pick your opponent's action. The opponent was trying to beat you at the game. And so you're trying to figure out what to do no matter what your opponent ends up doing. And so we had to reason about our action And then what they were going to do, which was the opposite of what we wanted, that was minimax, right? So we were trying to maximize, they were trying to minimize. And then we're trying to maximize. And then alpha beta pruning, where we prune that tree because we assumed once we figured out what the minimizer was going to do, that we knew the best we could bound the best that we could do, and we could stop expanding nodes at the leaves based on those bounds. Cool. So then uncertainty. That was our second unit. So we had these Desiderata, where you guys saw a video lecture. Sorry, I couldn't be there for that lecture. Degrees of plausibility, this was the Janes reading. Degrees of plausibility are represented by real numbers. Qualitative correspondence with common sense. And consistency. So if a conclusion can be reasoned out in more than one way, we want it to all come up with the same answer. And it always takes into account all of the evidence that it has that's relevant to a question. It doesn't arbitrarily decide to ignore stuff. And it represents equal states of knowledge by equal plausibility assignments. So these real numbers have to be kind of comparable to each other. If I know the same amount, then I have to be the same number and the same numerical value. And we talked about I'll move this down here, and what you get is the sum rule and the product rule. Probability of A and B given C equals probability of A given B and C times the probability of B given C. And the sort of intuition was that we wanted us to be able to, you can factor this in two different ways, and we wanted the different states of knowledge to sort of work out to be equal. So he derives this rule as like the way to do that. And then we wanted things to normalize right. So this was sort of coming from wanting to use real numbers to represent these quantities, and having equal plausibility to work out to be equal weights, and also having the product rule around. If you remember, there was two ways we could do this. We could have also had it go from negative infinity to 0, and the math would have all worked out to be the same, but I don't know if it's historical reasons or convenience, or it's just nice if you have 1s and 0s. Most of the time we talk about probability, we talk about going between 0 and 1, but a lot of times when you implement these algorithms, you actually use the other representation because it fits into our finite registers and memory addresses better. So you can, when these numbers get really small and you go to log probability, you don't hit overflow errors as quickly. So lots of implementations will use log probability for that reason. So we talked about Janes. And then we talked about graphical models. So this was our little robot trying to localize itself. So we were trying to estimate these types of probabilities and compute them. There was graphical models. So this is a model for localization where there's these different rooms it could be in, and then there was the bed, a microwave, a chair, a sofa. And we were trying to estimate our probability of being in different rooms based on these different observations. So read the model, write down the factored structure. And then tables. So we talked about the tabular representation for these probabilities. There's some tables. And then you can kind of get the marginals that you're interested in. So you should be comfortable kind of manipulating these tables, understanding these models. A lot of times when I'm thinking about graphical models, like in real problems, you don't usually use tables. You guys used EKFs, so Gaussians and stuff for the SLAM project. We use some kind of parametric form. But I find it sort of to sort of get a more intuitive understanding to go back to these tabular representations, because it just makes it very concrete what these variables are doing, what the different probabilities mean, and stuff. Talked about Bayes filters. This is the model for it. You should be comfortable with Bayes filters. So we talked in lecture about localization, then you guys did SLAM. How do we modify this if we want to do SLAM? What do we have to add to this model for SLAM? There's another variable that's missing. So here x is the state, so that would be like the robot's position, yeah? Yeah, so the controls are you, right? So that would be like where you move the robot to. So you can see the control input, the last step, predicts your state at the next step. Right? You're going to move from where you were, your previous state, and your control input predicts your next state as you move. Yes? There's no noise.
Like you're going to go to the next state versus not knowing where you are.
Yeah, so it depends on what you do, what your control model looks like. So here, we wrote it down. X sub t equals x sub t minus probability of x sub t given x sub t minus 1 and u sub t. So how might I model that if I want to take into account noise? So let's say x sub t, here's my robot. And it said 0, 0. So x sub t, that's x sub t minus 1, 0, 0. You guys can't see that. Sorry. I'll draw it over. Okay, so x sub t is 0, t minus 1 is 0, 0. Mu u sub t minus 1 is, let's say I'm going to go over 1 and up 0. So here's my little robot, and it's facing in this direction. This is 0, 0, this is x, and this is y, and I'm going to drive in this direction, over 1 and up 0. So how does it look if, how does my control model look if there's no noise? What should I do? What would my x sub t, in this world, what would my x sub t equal with this representation? Yeah, so if it's deterministic, it would just be 1, 0. Like, so if my control is going to be a drive to the right 1 meter, let's say this is meters, it's just going to work for sure. What if I want to put noise in there? What should I do? What could I do? What's that? Yeah, so somehow I want to write down the, oh, perfect, it's right. You guys can't read that either. I'll move it down just a smidge. You actually want a distribution over this. So this model here, you could have it be a distribution where every other value of x sub t besides 1, 0 gets 0 probability, right? But if I want it to be, and that would be sort of a deterministic version of state transitions. If I want it to be non-deterministic, I want to somehow smooth this. I want other values of x sub t to have non-zero probability. I don't want, I don't know, like maybe I want my robots to move perfectly, but in real life, it's not going to move perfectly, and I want my model to reflect that. So how could I do that concretely? What are some ideas for how to model that distribution? How do we do it in a SLAM project? You can sort of imagine that like this is like my target. This is where I think I'm going to be. So and there's a distribution on this, right? So you can think of it as like a graph that's coming out of probability mass, right? So the deterministic version, it's like a point mass right here, right? It's just sticking straight up here. Everything is in this one point, and everything else is 0. What is it going to look like if it's not a point mass? Yeah. Yeah, right. So one way, like so one way is to have kind of a Gaussian. So maybe I'll draw like the rings of it. You know, I have some kind of curvy thing, right? That's my video. Here's like an online video of the distribution. Right? I want to kind of spread the mass around a little bit, and a Gaussian is one way to do that. So I have a Gaussian centered at this point. The mean is at this point. So the hump of the Gaussian is going to be right at where the sort of idealized model says. But there's going to be error. So it's going to be kind of spread around according to the covariance. That's going to be how spiky or not spiky my Gaussian is. How else could I model this? Yeah, so I could say that there's a Gaussian in Cartesian space, or I could say, well, maybe my little guy is going to go off in slightly different direction, and it's going to stop slightly short. So there's going to be Gaussian or some other kind of noise model on that, right? And that'll translate to a different kind of uncertainty. What else? What if we stuck in Cartesian space? Is a Gaussian the only thing I can use? Is it? Is it the only thing I can use? Am I stuck with Gaussians? Is that the only distribution we know about? Gaussians or nothing? Yeah?
Could you discretize it and make it into just like a table distribution?
Yeah, I could. Yeah. So I could say, well, maybe there's like a bunch of different point masses. So I could say each one of those has some kind of probability. Make it into a multinomial. And I might want to do that if continuous space is too complicated. There's too many points in there. It might be a game, right? So maybe there is some noise in the game, but I know that I'm going to end up at one of those specific points. There's another model I wanted to mention, which is uniform. So I could decide that like I'm gonna drive over here, but there might be like a small probability that as I'm driving, at some point in there, my motors will just die. My batteries will die, and I'll stop. So how could I model that with a uniform distribution? Maybe like a couple of distributions that I add together. So I'm going to drive, and hopefully I get there. And if I finish my drive, I'm going to be right where I'm supposed to be. But if I don't finish, but my batteries might clunk out on the way, randomly. And I'll just be stuck. Let's say it's just one-dimensional. I'm going to go right along that x-axis. So what does that look like? Where could I end up if I do that? Where's the probability mass going to be in this curve here? I'll erase all the stuff that I drew so you can see it. So here's my little robot. I'm going to go for my drive along the x-axis. If everything goes great, I'm going to have a point mass right here. But if a battery dies, I could end up somewhere along the x-axis. So what is the probability mass? Where do I kind of intuitively want it to be in that model? Yeah, so there's going to be some small probability of something going wrong all along the x-axis. And if that happens, I'm just going to be here or here or here. But maybe most of my probability is nothing happens, and so there's still a higher probability at the end. So you might have a small uniform probability of failure and a big chunk up at the end. Actually, people use models like this for sensor error. So like a LiDAR sensor, if you're driving around and localizing, and there's people in the environment, and so you're localizing, and your sensor might have a Gaussian. Usually, you use a Gaussian model instead of a point mass for the sensor error. But if somebody walks by, the sensor's going to bounce against them and not against the wall, and you're going to get a reading that is inaccurate. It's going to be very improbable according to the Gaussian way out here, right? So that might mess things up. But if you add to your sensor model a small uniform probability of one of these crazy things happening, a person walking by your robot, it's crazy. Think about it. Then the localization algorithm will actually work better, because it'll be like, oh, I know what happened. Somebody walked by. I'm not going to downweight this particle too much in my resampling. And then the next time when the person goes away, then hopefully it'll get a better reading, and that particle will still be around to represent the true distribution. Cool. All right. So I guess we'll go like five or six more minutes, and then I'll hand out the surveys. And I'll need a volunteer to, is this them? I'll need a volunteer to take to take them and collect them. So we talked about prediction, Bayes filters. We kind of talked about SLAM, decision making. We kind of talked about this stuff at the beginning when we did the policy search stuff. So like estimating generative models, discriminative models, where you either estimate the conditional distribution or you directly estimate this function here. You can be entirely rational without actually doing probabilities. And then we did MDPs, so we talked about these transition functions and reward functions a bunch, so I won't cover it now. Bellman equation, value function, summing up our expected reward over time. And then value iteration, this was an algorithm. This was, remember, this was like the reason the term dynamic programming was coined for VI and its cousins by Bellman. I think I put up that thing in there. POMDPs. So when we don't get to observe the state, then we have to maintain a belief over our underlying state and then choose an action based on that belief. So a POMDP, the belief update's a Bayes filter. It's the same. Like there's a control input, which you get to know. There's a state, there's an observation function, there's a state transition function, and you're trying to estimate your belief over where you are. But what's different is you also, in sort of SLAM or localization, the actions are just handed down from somebody else. And a lot of existing SLAM work, almost all of it, they're driving the robot around. Somebody's joysticking the robot around as it builds the map. Or they're doing fairly naive strategies for exploring the map. Some of the newest work in SLAM is thinking of it more in a POMDP way where you get to pick the action. And you're trying to pick actions, pick places to go in the environment that enable it to collect information about spaces it doesn't yet know about. RL, policy-based, value-based, model-based. So we talked about that already. I won't go into it. There's slides. All right. So that's the sort of course outline. So I hope the review was helpful. Yes? No, the whole thing is cumulative. And the reason is we want the final to be helping you integrate your knowledge over the entire course.
Are you going to have to take part 1 and then turn it in?
Yes.
And then have
Yeah.
it separated? Okay.
Yeah. So it's going to be taking 2 exams, one on Thursday and one the following Tuesday. So you have the weekend to recover. Yes?
Do we know yet what the deal is with room assignments?
We'll stay tuned for emails. Part of it will be in here, but we wanted to have additional space for people, so we have rooms booked, but Miles is going to send an email with the logistics of that. All right, maybe we'll take like 5 minutes. I just wanted to ask you guys if you had any feedback from me about the course that you wanted to share or discuss for future iterations. And also I wanted to say I'm open, I'm very interested in hearing privately over email or also in your course evaluation surveys for how we can make the experience better in future semesters. Some things I've heard already, not that you're welcome to say it again too, but like I know SLAM was too hard, and we're definitely going to make that easier in future semesters. And we took your feedback about the midterm into account when we're making the finals, so we think it's going to be shorter, so maybe less trying to write as fast as you can. But I'm really interested in hearing your feedback about it. And also, we're looking, in the spring semester, we'll be looking for UTAs for the following fall. So if you enjoyed the course and you want to help make it better, definitely consider applying for being a UTA, because the course could not happen without the awesome UTA staff and grad TA staff that sort of answer your questions and help with creating the problems, the kind of the front lines in getting this material taught. So comments, questions, concerns? Yeah.
I really liked getting the immediate feedback on the homework. I thought it was really helpful.
Cool.
If I were right or not.
If it's okay, I'm going to just take notes. Oh, you are? Great. Thank you. Thank you, Betsy. Awesome. Liked feedback on the homework. Yeah.
I didn't really feel that SLAM was like too hard, more that like you didn't really know what you're doing.
Yeah.
Like, if the material had been more covered in class.
Yeah, I apologize. Yeah, that was Jay being sick.
I don't think
And
it was like too difficult. I think it was an issue. And I think the same thing happened with Tarmac, where I felt at least that I was kind of seeing like lead in the dark. And I was like fumbling around.
Okay.
Eventually, I like got this thing. Like I think this is right, but I didn't really feel like I understood why it was right. I just kind of got it.
Okay.
That was it.
Okay.
I've talked to people about the same thing about this.
Okay.
Like, I don't think the project either one was necessarily too hard. It was just an issue of not feeling like I was, the things I was accomplishing weren't because I was understanding materials, because
Yeah.
I was trying things.
Maybe we'll try to align the projects so that they're due farther after the lecture happened, so that you get all the material halfway through the project instead of by the end of the project.
Yeah, I think on a lot of the projects we were sort of given equations to use.
Yeah.
To have more information on how the movements came about.
Okay.
Well, it'll make it easier to discuss.
Yeah.
Oh, it's plus or minus.
Okay.
But also I think the equations are really useful.
Okay. Okay. We can definitely do that.
Yeah, for SLAM and also RMAX, there was a period where like a TA would just like talk to maybe 10 to 15 students like about the big picture
Yeah.
for 10 to 20 minutes.
Yeah.
If, like we could just have that at the beginning of the project.
Yeah.
That helps so much.
Okay. Okay. Yeah. So I think that's more about hearing it in lecture
Yeah.
at the right time instead of like right before it's
Addressing,
due.
like, the
Yeah.
project explicitly.
What's that?
Just like addressing
The project explicitly. Okay. Yeah. So better alignment between the lectures and the projects. Okay. Are you? Is this too fast for you?
Yeah.
That's what? Is this too fast for you? Okay. Great.
I think building off what Kate said, like
Yeah.
beyond like immediate feedback, I found the warm-ups really helpful.
Okay.
Just like be able to like trial and error before.
Yeah. Awesome. I'm glad that was good. More feedback? Yeah.
Also, with the search and RL projects, it was pretty easy to tell from the visualizations if you were doing those right or not.
Uh-huh.
But with SLAM, it was a lot harder
Yeah.
to tell. You could have a pretty broken implementation that
Yeah.
kind of looked like it was doing the right thing.
Yeah.
So it might be helpful to have some sort of
Examples of that.
unit testing with smaller components.
Yeah. Yeah. I also got that feedback during the project. So I've been thinking about ways to. It's actually pretty hard. Like it made me think about like when I've coded up similar systems myself, and like it's really a surprising amount of time that like when I'm building one of these systems is spent not on implementing the algorithms, but implementing visualizers and test cases and scaffolding so that you can see what parts are right and what parts are wrong. But I definitely think it's hard to just do that whole cloth, and I think we should be able to provide some more support code and guidance for you guys about what that types of structure looks like. So I definitely want to do that in the future semesters.
Along those lines, several of the projects, there were several things to test on, like the last one, RL, there were several levels to test on, but not expected results from anything
Yeah.
other than the easy level, which
Yeah.
wasn't as good of sort of a
Yeah.
idea of whether you
Yeah.
were right. And
Yeah. So more test cases.
give a couple more.
Yeah.
You should be getting.
Okay. All right, maybe one or two more, and then we'll hand out the surveys. Yeah?
So I met the prereqs for this course.
Uh-huh.
I felt that a lot of the math was just going way over my head. And
Okay.
I was managed to get here without having taken any true math courses yet. And so I don't know if that means that something like linear algebra should be added as a prereq for this course, or if something
Yeah. Yeah, so like the EKF updates and stuff? Yeah. Yeah, I didn't want to add linear algebra. I mean, it's no. Yeah, we were trying. I think we should try harder to make the SLAM project less about doing the right linear algebra updates and more about getting the probability stuff right. Something that I was thinking about was starting with localization first. So like it would make the project longer, but like it would give you kind of warm up of a Bayes filter without the map and without as many linear algebra updates. And that's another way to test the system. So like if you can localize yourself, then you know you've got a good transition model and a good state update model. And then you can try doing full-on SLAM where you estimate the map at the same time. So that's good feedback though. So we'll try to I think we're going to revamp the SLAM project for the next semester, and we'll keep that in mind. All right. Well, thanks, guys. Can I have a volunteer for collecting surveys? I think I hand them out. Here's the instructions. Pass out the surveys. Designate a student to hand them to give them back. So does anybody want to volunteer to collect them? I give you this envelope. Thank you. And then here are surveys. And then do I leave or do I stay? Okay. I think when I was a student, the instructor typically left to avoid biasing you, so you can feel free to fill it out however you want. Is there an instructor survey? I thought there was one that I do. Is it in there? No.
Was the pink one?
Oh, is it pink? Oh, this must be it.